Hi, welcome back. So today we begin chapter 4, the last chapter of the semester. So we're going to start with section 4.1, which is on maximum and minimum values and several different definitions and theorems that we need along the way. Just to kind of look ahead, this chapter involves a lot of things that we learned back from chapter 1, basically with rules on limits and derivatives. And also in this chapter, we're going to look at sketching from derivatives and learning some stuff about functions based on the derivatives. So a lot of stuff going back to the beginning of the class, okay? We're also going to look at our last application for derivatives, which is called optimization in section 5. And then we actually will end the semester with section 4.7, which is kind of getting you ready for calculus 2 and looking at antiderivatives. Okay, so a lot to do in chapter 4, so make sure you get a good start on this, keep up with everything, and do a lot of practice. All right, so for max and min values, the very first few definitions that are on this on the notes here actually stem back from what you did back in Algebra 1, Algebra 2. Okay, and that's the difference between what are called absolute max and min values and local or relative max and min values. So absolute maximums and minimums, also known as extrema, okay, have the definitions that say a function f of x has an absolute max at x equals c if f of c, which remember is the y value for that x value, so if the y value of c is greater than or equal to all other y values of f of x for every point that's in the domain. Same thing is true for an absolute minimum. You would have some value at x equals c where the y value is less than or equal to all the other values of y for every x in the domain. Okay, so very basic functions I can give you that you know that exists would be for a parabola. Okay, so let's say I give you this parabola. Here's function f of x, and then there's the maximum. So whatever this c value is, this is what this definition says. Here's c, right? X equals c, and then here's f of c. Okay? That's the y value. So what this says is as long as we can show that f of c, the y value of this point, is the highest y value of any other point in the entire function, then that would be an absolute max. Same thing holds true as if we had a parabola in the opposite direction. Maybe it did this. Okay, so here would be c, here would be f of c, and you can see very clearly that that's the smallest y value out of all of the y values in that function, so that would be considered an absolute minimum. Okay, so those we know for a fact because they're the absolute. There's nothing higher, nothing lower than those values. Okay. All right, on the other side of that, you guys learned about local max or local mins, or some books call them relative max, relative min. So same thing here, just depends on which textbook you learned out of and how they called it. So a local max, local min, relative max, relative min, same thing, okay? So look at the definition here. What's different about it? It says a function f of x has just a local maximum at x equals c if f of c is greater than or equal to f of x for every point x. So up until this point, that is exactly the same definition. For every point x, except this one was in the domain, and this just says for every point x that is near c, okay, near it. So in the local area, basically. Okay, and then the same thing for local minimums. F of c is going to be less than f of x for points x that are just near it. Okay, so what does that look like? Okay, so let's take a look at a function, maybe a cubic function. Okay, so let's look at that. Here's an example of a cubic function. right there, I know that's a max, and right here is a min, but they're not absolute, right? Because this function continues up forever, it's not going to have a absolute maximum. And because it continues down, it won't have an absolute minimum. But these right here are what we call relative max and mins, okay? So here would be a point C, I'll call that C1. So if you look at everything around C1, so maybe from here to here, okay, everything within this area, that would be the max. Okay, not for the whole graph, but just near C. And the same thing over here at this point, let's say that's C2. Then if I picked around C2, maybe this area, that would be the lowest or the minimum value within that area. Okay, so that's the difference between local and absolute. Okay, so pretty similar definitions, just kind of where we're looking at for the function. Okay, all right, so I know most of you know that, but let's move on then to parts C and D. All right, so C is the extreme value theorem, which is going to come in a lot for some of the problems that you do. So you just need to remember the extreme value theorem and what it says. Okay. So it says if f of x is continuous on a closed interval, okay, so between 2 points, these are your x values, then f of x, the y value, attains both a max and a minimum value on AB. Okay. All right, so what does that mean as far as what we're looking at? Okay, so let's take another picture. Let's say graph something like that. Okay, so here's a graph. This is function f of x. All right, f of x has to be continuous on an interval between a and b. So let's just say I have this be a, and over here this could possibly be b. Okay, so 2 points, 2 x values, and it's a closed interval, so we are including these points. So what this says is that between this point on the curve and everything to get to B, okay, so all of this, yes, somewhere in there will be a max value and a min value, okay? All right, so I'm going to write, because these values that you find don't have to necessarily be between them. It could be actually one of these. So I always put a little asterisk here that it could be at the end point. Okay, that might be your max or min value. You just have to figure it out, which we're going to learn in just a minute. Okay, so if I look at this graph, I can easily see that the max between A and B would be way up here. That's a point between A and B. Where's the minimum between A and B? It looks like the minimum would actually be at wherever A is, over here, okay? So you may have a max or min between A or B, or the max or min could be A or B, because you're including those as part of your answers, or part of the choices that you can pick, okay? So what this extreme value theorem says is no matter what continuous function you're given, if you're given an interval in that function, you can find a max or min between those two values, okay? All right, so that's called the extreme value theorem. And then the last thing on this page is called Fermat's theorem. And Fermat's theorem says if f of x has a local max or min at C, and the derivative at C exists, okay, then the derivative of C has to be 0. All right, so let's talk about that. If f of x has a local max or min at C. So I'm going to do 2 C's in this problem, just like I did before. So let's say, let's call this C1, there's a max, and let's call that C2, there's a min. Right? These are not absolute, these are relative max or mins, but they're max and mins, local, so they don't have to be absolute. All right, So we know we have a max here, okay? All right, we find the derivative of this point, okay? So the derivative has to exist. So remember, in order for a derivative to exist, we can't have any corners, we can't have any asymptotes, nothing like that, right? That to have a derivative. So as long as the derivative exists, then I know for a fact that this derivative will be 0. And we've known that for a while now because the derivative, remember, is the slope of the tangent line. And the slope of the tangent line of any max or min is horizontal, which means that derivative has to be 0, right? All horizontal lines have a derivative of 0. Same thing with a minimum. As long as I know that's the minimum and I can find a derivative, then I know the derivative of that tangent line, so f prime of C2 must also equal 0. Now, the most important thing about this theorem is you can't go backwards, okay? You can sometimes, but not always. So I'm going to put another asterisk here and write not the other way around. Okay, so what do I mean by that? So if you look at it the other way, just because the derivative at some point is 0 does not mean that you have a max or min. You could, you very well could, but you can't always assume that you do. So you can't read theorems backwards, okay? So yes, if you have a max or min and the derivative exists, definitely I know that derivative is 0. But just because the derivative is 0 does not necessarily mean I have a max or min. I could, okay, and there's other things I need to know about it, but that doesn't always hold true. Okay, so make sure that you kind of remember that as we move forward. Okay. All right, and I know I'm spending a little bit of time on these definitions, but these are really important for the rest of this chapter. So we need to make sure that we are understanding what these things mean. Okay. All right, now let's look at E, okay, which is critical numbers, and then this should be F. I think that's a typo. I don't know if that got fixed on your guided notes or not, but next letter up, okay. All right, so critical numbers. A critical number of a function f of x is a number c in the domain such that the derivative of c equals 0 or the derivative does not exist. Okay, if f of x has a local max or minimum at c, then c is a critical number. Okay, we know that because the derivative is 0, right? All right, so I'm going to write some things here to kind of help us as we go through these notes today. So when we're looking for critical numbers, we have to find where the derivative equals 0. So these are going to be your possible max and mins. Okay, possible, remember, because we can't go backwards. So remember what I said, just because the derivative is 0 doesn't mean they're max or mins, but they're possible max or mins, right? That's the backwards part. So we have to check that. And then where does the derivative not exist? Okay, that's still a critical number. Okay, so this is still a critical number. And think about where the derivative doesn't exist. Okay, okay, so that means that is either an asymptote or a number not in the domain, right? We got to check all of this stuff out. All right, so for a derivative of c to not exist, c, the number, the critical number, either it's going to be an asymptote or it's going to be a number that's not in your domain, okay? So we got to check that out as well. All right, so let's look at how we would do that. So I'm going to write a guess over here. I don't have a lot of room for this. All right, so to find critical numbers, okay? So critical numbers, what we need to do is set the numerator. If you just have a polynomial, we're going to set it equal to 0. We're going to solve it. That's not a problem. But when we have other kind of functions like rational functions, radical functions, different things going on, we're going to set the numerator equal to 0, and we're going to set the denominator equal to 0. Okay, these all give you critical numbers. Typically, these are the ones that exist and give you a derivative of 0. Typically, these are going to be your derivatives that don't exist. Okay, so just keep that in mind as we go through these. All right, and then the last thing before we get started on the work is how do you find an absolute max or min? So this is called the closed interval method. None of you usually have a problem with this. The only time I see that there's a problem is you forget to test the endpoints, okay? So to find an absolute max or min of a function between 2 points, okay, so not the entire graph, but just between A and B, okay, then you're going to find the values of f of x at the critical numbers, okay, so we're going to find the critical numbers. We're going to find the values of f of x at the endpoints. So remember, these are the y values, okay? We're finding the y value of the critical number, find the y value of the endpoint values, and then simply the largest of those will be the absolute max, and the largest will be, and the smallest value will be the absolute min. And remember, these are the y values, okay? Y values. Largest y value is the max, smallest y value will be the min. Okay, and then it tells you here that the closed interval method is used to find all absolute max and all absolute mins of a function over a closed interval. So anytime you're asked to find it, and the interval must be closed, not open. Okay, so little things, but all of those are important to what you're looking for. Okay, all right, so 1 and 2, Dr. Taylor did with you, finding the critical numbers, and those are just polynomials. And remember, polynomial is just basically finding the derivative, setting it equal to 0, and solving. Okay, so nothing special about polynomials. There's no restrictions on the domain. So, you just find them like you normally would. Okay, all right, then he did number 3 with you, which is a little bit different function. Okay, it's a rational function. So he showed you how to find those critical numbers, and we're going to do another one of those together. And then number 4 asked you to find the absolute max and mins given a closed interval between 0 and 6. So he also did that with you as well. Okay, so what we're going to do is start with number 5. This is another polynomial equation, but again, I want to just go through them with you myself so you know that how to do these. So hopefully you watched the intro video, and so you kind of have an idea of how to do these. So hopefully that will help you. All right, so this just asks for the critical numbers. That's it. Okay, what are the critical numbers? When you're asked just to find a critical number, that's just x. Okay. When you're asked to find the max and mins, then that's when you get y involved. So all we're going to do for number 5 is find the derivative of the function. So the derivative of this polynomial would be 4x plus 9. Okay. You're going to set the derivative equal to 0, and you're going to solve for x. So we're going to subtract 9 from both sides, divide by 4. Okay, so that right there is your critical number. Okay, so critical number, just the x value. If I wanted to know what the y value was for this ordered pair, remember that you plug this into the original function. You always use the original function to find y. Okay, always to find y, you plug it into the function. All right, so that's just another quick critical number using a polynomial. All right, now just look at number 6. Find the critical numbers for the following. All right, so again, we're going to find the derivative, set the derivative equal to 0, and solve. Okay, so derivative of negative 2x cubed, that's negative 6x squared. Derivative of 33x squared is 66x. Derivative of negative 60x minus 60. Derivative of 11 is 0. okay? All right, so I'm going to set this equal to 0, and as I do that, I'm going to factor out a -6. I don't like my squared term to be negative, so let's just factor out a -6, so that leaves you x squared minus 11x plus 10. Set that equal to 0. All right, so we're going to factor x squared minus 11x plus 10. Factors of 10 that add up to give you 11, that would be 1 and 10. Both would be minus. Now, for some of you, when you set factors equal to 0, remember what we're solving for. We're trying to find the x coordinates that equal 0. So -6 is a factor, but it's a constant. So it can never equal 0. Right? We're just trying to find what makes x equal to 0. So I have some of you that still want to set constants equal to 0. No. Okay, only terms, only factors with x in them. Now, if that was -6x, yes, you would set that equal to 0. But right now, that's just -6, so that's not one of my factors that I am concerned about. That's a constant. All right, so we're going to set x minus 1 equal to 0, set x minus 10 equal to 0, and solve. Okay, so we get 1 and we get 10. Okay, so again, these are critical numbers. So remember what that means. Those are possible maximins. Okay? Now, in this case, because this is a polynomial, okay, let's think about what that looks like. I didn't ask you to do this, but just so we understand. Those are the only two places on this graph where the derivative equals 0. Okay? That's what we just found out. And if you remember what a cubic function looks like, okay, it's negative, so that means the top would start up here. This is your y-intercept, so it goes through 11 up here. So this graph may look something like this. Now, I'm just sketching that, okay? So what this tells me is that right here, and I know I didn't draw it to scale, but you can kind of get my drift. Right here and right here at x equals 1 and x equals 10, those are the only two places on this graph where the derivative is 0, right? That's horizontal tangent lines. So that means that's your max and your min, okay? So at 1, there's a minimum, and at 10, there's maximum. So not only are these possible max and mins in this problem, but they are indeed some, okay? So that's why I said, just because you know the derivative equals 0, they may or may not be max or mins. It depends on the function. So this is just a polynomial function. That's typically what will happen, okay? But I want you to understand what it is we're doing, because in a few sections, we're going to have to use this information to sketch these things without kind of knowing what the function is, okay? So derivatives that equal 0 are your possible max and mins, because that's a horizontal line. That's the only kind of derivative that will give you 0 is a horizontal tangent line, okay? All right, moving on. Number 7. All right, this is one that was like number 3 that Dr. Taylor did. So just want to kind of go through another one with you. Actually, I think it even uses the same fraction. So let's find the critical numbers. Let's just make sure you're okay with this one. All right, now, you could do the product rule, or you could distribute first. Either way is okay. I'm just going to go ahead and distribute so that I don't have to do the product rule. Now, if you don't want to distribute and you want to just do the product rule, it'll still come out the same, but again, it just depends on what you want to do. So I'm going to just distribute. So x to the 4/5 times x. Remember, this is x to the first power. You add your exponents, and 1 is the same thing as 5/5. So we got 4/5 plus 5/5. So that's going to be x to the 9/5. And then x to the 4/5 times -5 is -5x to the 4/5. So that's the function. I didn't do any derivatives yet. This is still f of x. I just distributed. Okay, this times this times this. All right, that alleviates me having to do the product rule. Now I can just do the derivatives of the individual functions. All right, so the derivative of x to the 9/5 is 9/5. X to the subtract 1 from that. 1 would be 5/5. So 9/5 minus 5/5 is 4/5. Minus 5 is going to stay out front, right? And then the derivative of x to the 4/5 is 4/5 x. Subtract 1 from that. 4/5 minus 5/5, negative 1/5. All right, so if I clean that up a bit, I get 9/5. Well, let me write it where everything's in the top. So 9x to the 4/5, that's all in the numerator, 5's in the bottom. And then here, the 5's are going to cancel, right? So we're going to have a negative 4 in the top and x to the 1/5 in the bottom. Okay? All right, so that's what I'm going to set equal to 0. All right, now remember what we talked about. We got to look for where the derivative does not exist and then where the derivative equals 0. Okay, so here's one of the first times where we have to take this into consideration, because right here, okay, I cannot use 0, right? I can't divide by 0, so I can't use 0 in this problem, which means 0 is a problem, so that's where the derivative would not exist. Okay, so we're going to say at x equals 0, so that's a critical number. Okay, it's a critical number because I can't use it, and if I can't use it, there's no derivative there. Okay, all right, now where does the derivative equal 0? That would be to finish this problem and solve it. Okay, so to solve this problem, I'm going to take this negative 4 over x to the 1/5 and move it over to this side. So that would give me 9x to the 4/5 over 5 equals 4x to the 1/5. So I'm just solving this. Okay, so that's where I started. And then I just added this to the other side. And now to solve, remember, we're going to cross multiply. So we're going to do 9x to the 4/5 times x to the 1/5. And remember, when you multiply, you add your exponents. So this is nice, because when you add 4/5 plus 1/5, you get 5/5, which is 1. So 9x to the 4/5 times x to the 1/5 is nicely 9x. And 5 times 4 is 20. Divide both sides by 9. So there's your other critical number. Okay? So this had two critical numbers for different reasons. One critical number because it didn't exist in the derivative, right? Now remember, this is where the derivative doesn't exist. Let me back this up for 1 minute. Because those of you that are looking at the domain, if I come up here, I can use 0 in this problem. Okay? 0 is not a problem in the domain. Where it's a problem is in the derivative. And that's what we're looking for. Okay? So keep that in mind. Critical numbers, you've got to stop once you find the derivative. If there's some problems, then we got to worry about those numbers. Okay? All right. So hopefully that makes sense on the derivatives not existing. All right. Number 8. Find the critical numbers again. All right, so this problem is involving exponential functions. Okay. All right, so I could distribute, but it's not really going to help me in this problem. So I'm just going to go ahead and do the product rule. Okay, just looking at this, that's not really going to help me. So let's go ahead and find the derivative using the product rule. So we're going to start with the derivative of 6x minus 2, which is 6, times the second function, e to the negative 6x, plus the first function, 6x minus 2, times the derivative of e to the negative 6x. The derivative of e to the anything, remember, is e to the anything, times the derivative of the exponent, and the derivative of the exponent would be negative 6. Okay? All right, so if I clean that up, this is 6e to the negative 6x. Now I've got negative 6e to the negative 6x. I want to bring that out front to make that negative. Negative 6e to the negative 6x times 6x minus 2. All right, so I'm going to set this equal to 0 and solve it. So I need to do some factoring here. So I need you to kind of see. This is a term, that's a term, okay? So this has two terms. There's a one plus or minus sign in the middle. So this term minus this term. All right, so if you look at both terms, hopefully you'll see that they both have this in common. So I am going to factor that out, okay? So if I take 6e to the negative 6x out of this term, that leaves me 1 minus, and if I take the 6e to the negative 6x out of this term, it's going to leave me 6x minus 2. And I put that in brackets and parentheses because that minus sign is going to have to distribute through here. So this is what I want to set equal to 0. Okay, set the derivative equal to 0. Right? That's what I'm doing. Okay, so let's simplify this bracket. So 6e to the negative 6x. I've got 1. Distribute that minus through there. So that's minus 6x plus 2. So 6e to the negative 6x times, I've got negative 6x plus 3, right? 1 plus 2. All right. So I'm going to set each factor with an x in them equal to 0 and solve. And we're going to talk about this because anytime you have an exponential function and set it equal to 0, you're not going to get any answers. So let's talk about why that is. All right, so we're going to take 6e to the negative 6x, set it equal to 0, and negative 6x plus 3. Right, so there's our two factors. All right, we're going to divide both sides by 6, so that gives us still 0. And then to solve, remember, we're going to take the natural log. So if I take the natural log of both sides, the natural log of e is 1, and I'm left with just that negative 6x out front, and the natural log of 0. Okay? So remember, this does not exist, right? When you look at your log functions, you cannot take the log of 0 or anything negative. So this doesn't exist, so I can't solve the problem. So this one doesn't have a solution, okay? There's no solution for exponential functions when you set them equal to 0. That can't happen. So remember, exponential functions are all above, right? If I look at e to the x, e to the x is that, remember? Okay, so there's no way it's going to equal 0. And if I'm looking at this part, there's no way logs can be 0 because logs have to be positive. So this is your natural log graph, right? So however you want to look at it, you're not going to ever get solutions for those. So really, anytime you have a factor of e to the x, you don't even have to set it equal to 0 because there won't be an answer. So all we have for critical numbers is on this side. So we're going to solve that, move the 3 over to the other side, divide by negative 6. So that's going to give us a positive 1/2. So this is your critical number. Now remember, that's a possible max or min, right? Don't know what it is because I have no idea what this function looks like. But the interesting thing is, if you were to graph that, crazy things happen with e, but here at 1/2, this graph kind of comes along here and then it kind of levels out. So there is kind of a point right here where it is a maximum that will have a derivative of 0. So it actually is a max of this kind of graph. Again, may or may not be, but just so we kind of see what's happening. All right, let's look at number 9. All right, so this one now we're going to use that very last definition that we had on the first 2 pages on how to find our absolute max and absolute min values, okay? Dr. Taylor did one of these with you on the intro video, so we're going to do this one. So pay attention to the fact that they're giving you this function, 3x squared minus 6x plus 8, on a closed interval between 0 and 10, okay? So remember the steps to do this, okay? So we need to find our where the derivatives equal 0, okay? So the first thing we're going to do is find the derivative, which is just simply 6x minus 6. We're going to set that equal to 0, and we're going to solve that. So 6x equals 6, x equals 1. Okay, so this is a critical number. All right, so what we're supposed to do now to find absolute max or mins is find f of the endpoints, okay, and find f of any critical number. So I have to find the value of this function at 0. I have to find the value of this function at 10. And I have to find the value of this function at its critical number 1. Okay? So I'm going to put 0, 10, and 1 into the original function. Do not use the derivative to find y. You always find y with the original function. That's a very easy mistake to make, okay? The only time we're going to plug x into here is if we're doing something with the derivative. But we're trying to find y. Y always comes from the function. All right, so put 0 in here. So 0 squared times 3 is 0. Minus 6 times 0 is 0 plus 8. So f of 0 is 8. Plug 10 in here. 10 squared is 100. 100 times 3 is 300. Minus 6 times 10 is 60. Plus 8. So this is 240 plus 8, so that's 248. Plug 1 in here. 1 squared is 1 times 3. Minus 6 times 1 is 6 plus 8. So that is negative 9. No, it's not. That's negative 3 plus 8, which is 5. Sorry about that. All right, so we need to find the absolute max of f of x. So what is the absolute max? That's a y value. So the absolute max is 248, and it occurs at x equals 10. So remember, the max is your y value. Where does it occur? That's your x value. All right, what is the absolute minimum? The absolute minimum would be 5, that's the y value, and that occurs when x is 1. Okay, so one of your minimum happened to be the critical number, the maximum happened to be an endpoint. Okay, so remember that can happen. Okay, all right, so we're going to do the same thing with number 10. Okay. So we're going to consider this function and look at our interval between negative 9 and 4. So we also have to test these points as well. So first thing, find your critical numbers. So find the derivative. So that's 6x squared plus 36x minus 162. Right, there's your derivative. Okay, set that equal to 0 and solve it. I'm going to factor out a 6 from each number. So that gives me x squared plus 6x minus 27. Factor. So factors of 27 that subtract to give you 6 would be 9 and 3. 3 would be negative and 9 would be positive. Set those equal to 0 and solve. Remember, you don't want to set the 6 equal to 0. That's a constant. So we have 3 and negative 9. So there's your critical numbers, okay? Those are both critical numbers. All right. Now, I need to test f of these numbers and then f of the endpoints. Now notice my endpoint actually happened to be a critical number, so I don't have to test it twice. So I need to find f of negative 9, f of 4, and f of 3. And it doesn't really matter the order that you do these, right? As long as you include them all. So I need to find the y values for these two, y values for those two. So happened that I had negative 9 twice. So I only have to find the y value once. Where are you putting these numbers? You're putting them back into the original function, right? So we're going to plug in negative 9 into here, okay? I did these on my calculators. So I just did 2 times negative 9 cubed plus 18 times negative 9 squared minus 162 times negative 9 plus 9. Just did that in my calculator. So I ended up getting 1,467. That's why I did it on my calculator. All right, same thing for 4. 2 times 4 cubed plus 18 times 4 squared minus 162 times 4 plus 9. Put that in your calculator. That gives you negative 223. And then I'm going to do the same thing with 3. You could actually put this into y equals and then just go to your table and get these numbers. That might be quicker. So 2 times 3 cubed plus 18 times 3 squared minus 162 times 3 plus 9. Plug that into your calculator, and that gave me negative 261. Okay, so once you have all of your values, you can find the maximum. Biggest value would be 1467, and that x value was negative 9. And then the smallest value would be negative 261, and that happened at 3. Okay, so again, most of you guys are fine with finding max and min values. You just have to remember to test all the points. Okay. All right, number 11 will be everybody's favorite because we're going to do the same thing, but we got a trig function now. Okay, if you have a trig function, just remember when you're finding y values, decimals are fine. Just make sure your calculator's in radian mode if you're going to be plugging in these numbers. Okay, typically the values are going to be on the unit circle, but if we're trying to compare y values, then I would say use the decimals because that's obviously, we understand that a little bit easier to kind of put them in order, right? All right, so let's talk about critical numbers first. Let's find the derivative, and we need to let the derivative equal 0. So let's find the derivative of this function. Derivative of x is 1 plus, leave the 2 there, right? And then the derivative of cosine is negative sine. So that's going to give us 1 minus 2 sine of x equals 0. So we're going to solve that, okay? All right, I'm going to go ahead and move the 2 sine of x over to the other side to make it positive. Divide both sides by 2. All right, so remember, we're looking for the angle. This is the angle, this is the ratio. So to find the angle, we're going to take the inverse of each side. All right, so remember your unit circle. Where on the unit circle is the sine equal to 1/2? Okay, the sine is the y value. So that would be over here at pi over 6. Remember, that's the square root of 3 over 2, 1/2. And then there's another place on the unit circle over here at 5 pi over 6. That's the ordered pair, negative square root of 3 over 2, 1/2. So there's 2 places on the unit circle where the sine is 1/2. And remember, this says only between 0 and pi. So both of those fall between 0 and pi. So we have 2 answers, pi over 6 and 5 pi over 6. Okay, so we have to test our endpoints. We need f of 0, f of pi, and then we're going to do f of pi over 6, our critical numbers, and f of 5 pi over 6. Okay, so remember, these are your critical numbers. All right? All right, so same thing. I'm testing my endpoints here, and I'm testing 5 pi over 6 and 11 pi over 6 here to find my max and mins. So this would be a case where I would probably put this in my calculator, go to y equals, clear that out. All right, so let me stick this here for a minute. So in y equals, I'm going to put x plus 2 cosine of x. Remember, original function. Okay, original function. All right, I'm going to go to my table, clear out. Oop. Why is that not going away? There we go. All right, I cleared all those out. All right, so I'm going to put in, stick that over here, 0. Okay, I'm going to put in pi. I just put in pi, it'll change it to a decimal when I hit enter. I'm going to put in pi divided by 6, so second pi divided by 6. So you can see I'm putting it in. So change it to a decimal. And I'm going to put in 5 pi over 6. Okay, so 5 pi over 6. So there are my y values, 2, 1.1416, 2.2556, and 0.88594. Okay, so still using trig, but since I have to order these and find the max and the min, it's easier obviously to do the decimals, which is fine. So find the absolute max and find the absolute min. So which is the highest, largest value? Right there. So this is our max. Find the least of those y values, and that would be our min, right? So doing the same thing, just wanted you to have a trig function to work on. So, okay, so don't shy away from these. It's still the same process, still do the same thing. All right, very last problem, multiple choice. Choose the best reason that this function has neither a local max nor a local min. All right, well, let's look at what we have. The function f of x is always positive, okay? That doesn't really matter whether or not we have a local max or min or not, right? So that doesn't really matter. So I'm going to rule that one out. That has no bearing on anything. The derivative of f prime of x is always negative. If the derivative is always negative, okay, that means the slope is always a negative number, which means your tangent lines are always going like this, right? Tangent line. So that means your graph is always decreasing. Okay. If your graph is always decreasing, then it wouldn't have a max or min. So that's a possibility. The derivative f prime of x is always positive. Well, if your derivative is always positive, that means the slopes are all going, tangent lines are going this way. This would be a graph that's always increasing. A graph that's always increasing would not have a max or min, okay? So that's a possibility. The highest power of x in f of x is odd. Yeah, again, that doesn't really have any bearing on what I'm doing because an odd function, that just tells me what the function's doing, but not the derivatives. To find max and mins, we are talking about a derivative. So that can't be. All right, well, let's look at the derivative then. Looks bad, but it really isn't. So the derivative of x to the 91 is 91x to the 90th. Derivative of x to the 25th, 25th x to the 24th. Derivative of x to the 7th, 7x to the 6th. Derivative of 13x, okay? All right, so now let's look at your derivative. This is always positive, right? No matter what x is, positive or negative, when you raise a positive or negative number to an even power, it becomes a positive number, right? So x to the 90 will always be a positive number, whether x is positive or negative. X to the 24th will always be a positive number, whether x is positive or negative. Same here, and 13 is always positive. So if we've got all these plus signs and all these numbers are positive, when I add positive numbers together, I get positive value. So that means the derivative is always positive. That means this graph is constantly increasing, whatever it's doing. Could be going like this, right? But it's constantly increasing based on this derivative always being positive. So that means that's why this thing doesn't have a max or min, okay? So took a little time to discuss that with you, but I want you to understand again, because we got to start sketching curves in a little while, what the derivative is telling you, okay? So if a derivative is always positive, numbers are always positive, then your graph is always increasing. So if it's always increasing, can't have a max or min, okay? All right, so that does it for section 4.1. So let me know if you need any help, work on WebWorks. Make sure you get your notes checked done, and I'll see you back here next time.